one of the more useful applications well, in this case it'll be geometric series, is in finance calculations. You might remember way back in, or year 7 might have been primary school, whenever you first looked at percentages anyway, we came up with this idea of simple interest, which was simply that the interest is PRT, where I is the total amount of interest, P is the principal, and R is the interest rate written as a decimal or a fraction, and T, of course, is the time periods. So if we had $3,000, 7 years, 6% simple interest, what will be worth after 7 years? So we just simply sub into our formula. But this works on the assumption that 6% interest is you just get 6% of the principal. So you get the same amount every single year. And of course, reality is you don't do that. But under a simple interest formula, you'd get, well, that'd be its value. So then later on, we saw a thing called compound interest, which of course is more realistic to what actually happens. Because of course, once you get interest into your account, then the next time they charge interest, you're going to get interest on your interest. So the compound interest formula, now that we've looked at geometric series, if you look at it, that's exactly what it is. It's a term in a geometric series. So you've got PR to the power of n, but it is in that form of AR to the n minus 1. It has that same feel to it. So this one calculates the total amount, so the original amount plus the interest. P is still the amount we've invested. The interest rate here, however, is not just the interest rate, it's 1 plus, because we're growing at a certain percentage. So the actual ratio is 1 point, and then the interest rate. And n is the number of time periods still. Now, when we are compounding, we need to make sure that the interest rate and the time periods match up, right? Because you're getting interest on your interest. So we need to make the time periods match up to however frequently they're compounding. Same question, but this time we're using compound interest. First time, let's assume it's compounded annually. So it's just a matter of subbing into our formula, and we see 4,510.89, which is more than the simple interest, because now we're getting interest on the interest. But if we compound more frequently, so let's say monthly, then we should expect it to grow again. But now we have to change the interest rate, because whilst they quoted 6% per annum, if we're compounding monthly, fortunately 6 divides by 12 very nicely, we get 0.005 there for our interest rate as a decimal. And the number of time periods is no longer 7 years, but 84 months. And so when we do all that, we see that, we get slightly more, about another $50 by compounding monthly rather than annually. So I say it should be a decimal or a fraction. That worked out nice, because 6 divided by 12. But if the interest rate was something like 7, then I'd leave it as 7/12 and use a fraction. Or 7 over 1200 it should be. Depreciation then, it's basically the same thing. It's exactly the same formula, but now for interest rate, instead of saying plus the interest rate, we're saying minus the depreciation rate. And so it'd be 1 minus the depreciation, because we're getting smaller and smaller. So the percentage would be less than 100% each time we apply it. So other than that, it's exactly the same. Depreciation rate, time periods has got to match it. So, and espresso machine. They tell me that's a coffee machine. So $15,000. Whoa. I knew there's a reason I didn't drink coffee. $15,000. Depreciates at a rate of 12.5% per annum. What's its value going to be in 2010? So 12.5, I'm going to have to, it's per annum, so it's all right. I don't have to do anything with the interest rate. But remember, it's 1 minus 12.5%, hence the 0.875. And it's 9 years. And so there's its value, $4,500. So that was sort of the basic compound interest, depreciation type questions that we might have looked at. I don't know, when was that, year 9, year 8, something like that. Here's another sort of question. They might say, okay, when's the value going to drop below 10% of its original cost? And we might have looked at those sort of questions once logarithms were introduced, or if it was before you knew about logarithms, you did it with trial and error. And so we want to solve that particular exponential inequation. Log both sides, bring the end to the front, dividing by log of 0.875, but just like we talked about the other day, log of something smaller than 1 is actually a negative number. So we change the sign. So it's greater than 17.24. So it'll be in the 18th year. So 2018. So let's get to the idea that we like to play with in, I guess, the student idea of superannuation. So investing money, regular instalments. So this comes from the 2002 paper. So as a superannuation fund, interest rate of 8.75% per annum. It is a very simplified model. It assumes that the superannuation fund pays the same interest rate for the whole life. Or another way to think about it is they've averaged out the percentage. The reality is, depending on how the superannuation funds invested the money, 1 year it might return 10%, another year it might return 5%, and so on. So they've just given us an average here over the length we're talking about. So 8.75%, compounding annually, so they'll pay that annually. $5,000 in the fund, beginning each year, starting 2003. So what will be the value when they're going to retire? Gosh, retire in 20 years. Be all right, I only had to work for 20 years. Okay. We've got to look at each investment. That very first investment that was made will be invested for 21 years. And so if we were to work out its value, it'll be 5,000, 1.0875 to the power of 21. But then the next year, going to make another investment. That one will be in there for 20 years. So similar, but the power will change. And then the next year, another investment. It'll be in there for 19 years. And so on and so on and so on, till we get to the last investment, which will just be in there for 1 year. And so the total value of the superannuation will be all these investments added together. So the total amount, and then we can see we've got a geometric series there. Okay. So the first term is 5,000 times whatever 1.0875 times by that. The ratio also is 1.0875. Number of terms we have is 21. So we're basically saying, what is the sum of 21 terms? And so summing it into our formula, we get our value for the investment. So a variation on this problem, you'll notice I put an asterisk there. This probably would be more like a question that you might see in an extension, a bit hard for TUNIT, I think. So find the year when the fund first exceeds 200,000. So we're saying, righto, we know the amount will be 5,000, 1.875. The last year's investment will be that. I'm sort of working backwards. I don't know how long this has gone for, because we want to find when it first exceeds. But I'm going to say it's in there for N years. N years will be when it first exceeds. So that first investment will be in there for N years. So that's why it's the power of N. And it will work its way back down, just like we did in the other example, until the last investment's in there for 1 year. So I know I'm going to get a very similar pattern as to what I had before. The only difference is I don't know what the highest power is going to be. That's what we're trying to find. So I know, okay, it's going to be a series that looks like this. So it's sum to N. I just don't know what N is. But we're saying, when is the sum to N greater than 200,000? Okay, well, there's the inequality we have to solve. Looks horrible, but it's actually not too bad. It really is just another one of our exponential ones once we tidy it up. So multiply, get rid of the fractions, divide by the other ones. Even though these are decimals, it does tidy up to be a nice neat fraction of 280 on 87. Add 1 to both sides, and there's our exponential we have to solve. So we can log both sides, get the n out the front. This time we're okay with inequality sign, because I'm going to divide by the log of 1 point something, so it's bigger than 1. Divide by that, and we get 17.1605, etc., etc., etc. So n is 18. So 2021 will be the first year when the fund exceeds the $200,000 mark. All right, another interesting variation on the problem. Just say I'm trying to work out how I can get $1 million. So I want to retire 31st of December 2020 under those conditions. I want $1 million when I retire. How much do I have to put in each year? So this time it's the actual installment I don't know. So my series again will be identical to what I had before. The difference now being, well, 2020 is 18 years, so the highest power I know is going to be 18. But now I don't know what P is. I don't know the amount I'm going to invest. That's what we want to find. All right, so the first term will be P outside of that. R 1.0875, N is 18. We're saying, when is the sum to 18 going to equal $1 million? Sub it in, and there's our solution. Of course, we can't tell quite now because we've got to get P by itself. So all I've got to do is multiply by 0.0875 and divide by the 1.0875 times the 1.0875 to the power of 18 minus 1. Whatever that all turns out to be should be the amount we're going to invest. So it works out to be almost $23,000 each year, which I suppose makes sense. If you want $1 million after such only 18 years, you're going to have to be investing quite a bit each year there to do that. So with each sort of question, it really is just working out, well, what is my series? What's the unknown that I'm trying to find? Now, I only bothered creating the series once at the very first part of the question. Once I knew the pattern, I didn't bother working out the pattern each time. I knew what it was. I just changed the numbers to suit the question. But they do like you to construct the pattern. So like I did where I said, oh, well, the first investment will be in there for so many years and so on. So it's not like you've just pulled this pattern out of thin air. You can sort of explain why you're creating this particular pattern. Loan repayments. Now this is the one that's really useful. The amount still owing after n time periods will always be this. So this is the basic idea. Amount n, I'm going to call the amount owing after so many time periods of the loan. And it'll always work out to be the amount I originally borrowed with the interest rate applied minus the amount that I've paid back with the interest rate applied. And that will always tell me how much I've still got to borrow. Or still got to pay back, I should say. So, Richard and Kathy are going to the bank. $20,000. Oh, going on a nice holiday. $20,000. Interest charged at 12% per annum, compounded monthly. They start repaying the loan 1 month after taking it out. Well, that makes sense. I mean, you're not going to start repaying it straight away. What will be the point of that? Here's $20,000. Can you give me your first repayment? Thank you. That's just silly. So, yep, that makes sense. And their monthly instalments are going to be $300 a month. How much will they still owe at the end of 6 years? Okay, so the initial loan, we always got to work out the initial loan with the interest rate. Now, if 6 years have passed, then the initial loan plus the interest rate, well, 6 years, we're talking monthly, so it's 72 months. Interest rate, oh, how nice, 12 divided by 12 happens to be 1. So 1.01 to the power of 72. So that'll be the initial loan. Okay, but as I say, what a repayment really is an investment. It's an investment on the loan that you took out. Okay, I'll explain a bit more about that later. So the first repayment, it's like saying, I'm going to give the bank $300 and I'm going to give it to them for 71 months. So it's 1.01 to the power of 71. So it's exactly the same as the investment problem we looked at, the superannuation idea. The second repayment will be invested for 70 months. $300, 1.01 to the power of 70. And then we'll keep going. Now, The second last one, this is where it's different to superannuation. It's the second last one that'll be invested for 1 month, and the last one will be invested for 0 months. Because once I give you the last repayment, that's it, we're done. So unlike the superannuation, where you still have the investment, the last investment is in the bank for a month, when it comes to repaying the money, the last repayment, that's it, we're finished. I don't owe anything more, so you're not going to charge me any more interest. So that's the difference between the two. So the last repayment will actually be there for 0 months. Now, why do I say repayments are an investment? When the bank gives you a loan, it's like they're saying, I'm investing in you. I've got money and I'm going to give you money. Okay? But for my investment, I want you to give me 12% per annum. That's how much my investment in you will get. So when I go back to the bank and say, all right, I'm not going to give you your $300 repayment, I'm now saying, here's my money, I'm giving it to you to the end of the loan. And so I get the interest rate of 12% per annum. And so that's why the amount owing will always be the difference between the two. The amount the bank has invested in me minus the amount I've invested in the bank. And that's why whenever you do take out a loan, certainly a big loan like a housing loan or something like that, if you can make more payments, then you'll save a lot of money, because every payment is like an investment. And say you're taking out a loan, housing loan, something like 30 years now, even more, some of them now. So if I say, well, I've still got 25 years to go on this loan, I'm going to pay an extra $1,000. It's like saying, I'm investing this $1,000 with you for 30 years. And so you will get the interest rate times that. So actually, even though I'm just paying an extra $1,000, I'm getting the extra $1,000 with the interest rate applied for however many years are left on the loan. And consequently, the loan will get paid off earlier and so on. So you try and maximise it. It's also why, because of compounding, if you have a choice, which most banks will do, if you have a choice between, do you want to pay your loan off monthly or fortnightly, you go fortnightly every time. Because even though it's fortnightly, it's still the same amount of money, just divided by 2. But because it's been compounded fortnightly rather than monthly, the investment is greater. So I'm giving the money back more frequently, it's being compounded more frequently, so my investment is bigger. So if they offer it to you weekly, it's a bit unusual, but if you can get one that does it, will compound weekly, obviously go for that too. That doesn't have as much effect. The reason the monthly one works the fortnightly one works really good is because if you pay back monthly, there are 12 months in a year. If you pay back fortnightly, how many fortnights in a year? 26, not 24. So it's like making 2 extra payments as well. Okay, so let's look at this problem. Principal plus interest minus instalments plus interest. So we worked out the principal was the $20,000 with the interest rate applied, minus all my repayments. We're just talking about for 6 years. So after 6 years, let's do the sums on that. Well, there's my series in here. Some people like to take out the common factor of 300 and just make A equal 1. It doesn't really matter when you think about it, because once you sub it into the formula, A will be outside of R. If you took the 300 out, you're just going to have 300 out the front anyway. So just a personal preference how you want to do it. So subbing in, calculating, and there it is. We've still got $9,500 to go. How much interest then have they paid in 6 years? Well, in 6 years, I've given the bank back $21,600. Okay. I've reduced the loan. So therefore, the difference between the two, 21,600, the amount I've paid back with how much I've actually reduced the loan by, tells me that must be interest. That difference between the two amounts must be the interest I've paid. Yeah? What I'm saying is, I've given the bank back $21,600. Here you are, I've given them that much. However, my loan has only been reduced by $10,470. Okay? Because we know we've still got 9,529 to go. So I've reduced the loan by that, but I've paid them that much money. So the difference in the two must be the bank's profit, their interest. Okay, let's again change the problem up. Let's say we had to find the amount of each instalment. We want to work out, we know how much we want to borrow, we know how long we want to take the loan over, but how much do we have to pay back? That's usually the sort of calculation we need to know. So YOG borrows $30,000 to buy a car, going to 5 years, 60 equal monthly instalments, interest rates 9%. So how much are my monthly instalments going to be? So don't know what it is. This is what we're working out. So I'll just call it M for monthly instalment. So the initial loan, so the bank is going to give me $30,000 and it's giving it to me for 60 months. And the interest rate will be 9 divided by 12, so 0.0075, power of 60. So that's how much the bank's lending me. My first repayment then will be invested for 59 months. Second repayment, 58 months. And so on and so on. But remember, it's the last repayment will only be there for 0 months. 0 months. So we know the amount owing at any point. So amount 60 we want, because when do we pay the whole thing back? After 60 months. Will be this expression here. So the amount the bank lent me with interest rate applied minus all the money I've paid the bank with interest rate applied. And so the first term here is just M, but the interest rate's 1.0075. Number of terms there, 60. And we can sub into that formula. But we know what amount 60 is. What is it? 0, because it's when we paid the loan back. So we can now solve this equation and find M. Rearranging all the terms, eventually, there we go, $622 a month and 75 cents to pay that one off. All right, this time we'll make the problem, how long is the loan going to be? So we know how much we can afford to pay. We know what the interest rate is. We know how much we're going to borrow. How long am I going to be paying the bank back? This was 2005. Now, councils obviously borrow a lot of money. How many zeros there? So it's $3 million at the beginning of 2005. Interest rate, again, nicely 12 divided by 12. Each year, the interest rate calculated on the balance at the beginning of the year, added to the balance owing. Debts to be repaid, equal instalments of $480,000, but that's an annual repayment. They gave us a bit of help with this one in the HSC. They said, show that the amount 2 will end up being this expression here. So the amount after 2 years. So the initial loan was for $3 million, but we're saying after 2 years with interest rate applied, that'll be 1.12 squared. My first repayment will simply be invested for 1 year. And then my second repayment for 0 years. So principal plus interest minus instalments plus interest. There we go. It is actually the same thing. We just got to convert it into scientific notation and factorise the second parentheses. But I mean, 3 million is 3 times 10 to the power of 6. 480,000 is 4.8 to the power, times 10 to the power of 5. So we have got the answer. We just need to convert it in the format they want us to show. Show that amount N will end up being this expression here, 10 to the power of 6, 4 minus 1.12 to the power of N. Okay, initial loan, borrowed for N years. First repayment will be there for N minus 1 years. The next one will be N minus 2 years, and we'll keep going until we get to the last repayment, which is there for 0 years. Same idea, principal plus interest minus the instalments plus interest. There's our expression. We have to show it's the same as that top one there, 10 to the power of 6, and so on. Well, let's play with our series. This time I did factorise out the 480,000. Although for some reason I still wrote down first term's 480,000. Go figure. Okay, the ratio is 1.12. Number of terms is n, of course. Subbing that into our formula. There we go. Now, not quite what they want, because they have grouped, you'll notice, the 1.12 to the power of n's together. So I've got to group the 1.12 to the power of n. But nicely, the 0.12 divides into the 480,000 and leaves a nice, neat, round number there, you'll notice, of 4, is that a million? Yeah, 4 million. So I've got 3 million, yeah, too many noughts, trying to get them all there. 3 million minus 4 million, and then plus just 4 million at the end. So I've got the 4 million minus a million, factorise out the million, which is of course 10 to the power of 6, and we have the expression that they wanted for amount n. So it then said, in which year will Wheelbarrow Backshire Council make the final repayment? So now we just have to solve when is amount n equal to 0. So solving this little equation. I guess they set it up this way because remember it is a 2-unit question. So it's quite difficult, that question for 2-unit, would be considered. So if they couldn't come up with this sort of expression, at least they could go and answer part 3 because all they've got to do is make it equal 0 and they could get some marks. And eventually log both sides and we end up with 12.2325 and so on. So the 13th repayment, which will happen at the end of 2017. All right, so 7B, 7C, 7D. I've just picked 4 out of each. If I remember correctly, 7B, that's probably just on simple interest, maybe. 7C might be on the superannuation and D on the time payment.